Hey everyone, in this video we're going to talk about section 1.6, which deals with exponential functions. First, let's begin with the definition. Let a be a real number where a is positive and not equal to 0. Then the exponential function with base a is the function f of x equals a raised to the x power. This is just a basic form, because exponential functions may also have coefficients in front of them that could be positive or negative, which we'd write as f of x equals to c times a to the x. So in this case, c is a constant coefficient in the front, a is the base of the exponential function, and x is the variable exponent. So just to be careful, recall that the constant c is not being taken to a power of x, only the base of a is. If you need a refresher on the properties of exponents, go back to the section 1.2 video. It's worth mentioning why we impose certain rules on the base of a. We require that a is positive and not equal to 1. First of all, the reason that we require a not to be equal to 1 is because this would simply just give us the function 1 to the x, which is just the constant function 1. And basically there's just nothing interesting happening here, or nothing to study. We also require that the base of a is positive. Even though I can compute a value like negative 2 to the third power, we understand that that power of 3 means multiply negative 2 by itself 3 times and I get negative 8. But what about negative 2 to the pi? What does it mean to multiply a negative number by itself pi amounts of times? The short version is that negative 2 raised to the pi is not defined as a real number. So we just simply require that all of our bases for exponential functions to be positive. We'll start by showing the graph of f of x equals 2 to the x. We're going to plug in x values from negative 1 to positive 3, and then we're going to plot the corresponding coordinates. When we do so, we'll get that negative 2 has output of 1 over 4, negative 1 has output of 1/2, and so on. When I plot these points and sketch the curve that fit these points, I'm going to get this curve-like shape that seems to hug the x-axis on the left and then shoot off to infinity on the right. It turns out that this function is going to have a horizontal asymptote of y equals to 0, which it never crosses. And then it's going to approach positive infinity as x gets very large. Similarly, we'll do the same thing for the graph of g of x equals 1/3 times 3 to the x. Here, that 1/3 out front is that constant multiplier that I was telling you about in the last slide. That 1/3 is not being taken to a power of x, only the 3 is. But let's get a feel for what this graph could look like. So for each of these inputs, I'm plugging in the corresponding value of x, and then I'm simplifying the entire expression. When I plug negative 2 into 3 to the x, I'm going to end up with 1 divided by 9. But I have that constant multiplier of 1 over 3 out front, and so that's going to give me 1 divided by 27. So the negative exponents are giving me all these fractions. And again, if you need a refresher on how the exponential properties are working here, go back and look at the section 1.2 video. But now that I've got these x and y values, let's go ahead and plot them and sketch the curve. So when we do this, you can see that the graph that we're getting versus the graph that we got above really are not that much different. It turns out that a lot of exponential functions do look very, very similar even when we're graphing them right on top of each other, and that is to be expected. Basically, exponential functions are a lot easier to graph than the rational functions that we saw in the last chapter, because there's only so many things that you can do with them, and you're more or less going to get the same kind of shape every single time. But these two examples showed what happens when I have a base, like 2 or 3, which is bigger than 1. In the next slide, we're going to look at bases that are less than 1. So start with the function f of x equals 1/2 raised to the x power. We'll do the same thing with our x and y chart, and we'll plug in each of these x values from -2 to positive 3, and we'll get the corresponding function outputs. And just like before, we're going to plot each one of these points on our x and y chart and try to sketch the curve. Once we do this, we can see that the curve is almost identical to the one that we saw in the last slide. However, it's going in the opposite direction now. It's almost like I took the mirror image of it. But we do have some similar properties. I still have a horizontal asymptote of y equals 0 that I'll actually never cross. And my graph is going to approach positive infinity still, but on the left side of the xy plane instead of the right side. For our next function, let g of x be 3 times quantity 1/3 raised to the x power. So here that 3 is a constant multiplier out front, but it's my 1/3 that's being raised to the x power. We'll plug in the same x values from -2 to positive 3 and look at the corresponding outputs. When we plot the points on the xy plane and sketch the curve, again we get a very similar graph to the one that's above. The changes are pretty subtle. The idea is that one is just a slightly taller version of the other, but it's kind of hard to see that when you're drawing these and with the naked eye. But the whole point is that exponential functions are going to be relatively predictable in how they look. They're all going to have more or less the same curve. It's just going to be a matter of whether the curve goes up when we read from left to right, or whether it goes down when we read from left to right. The next slide will help us categorize a few things. So let f of x be given by c times a to the x. Then we essentially have two possible outcomes for the graph. The first is what happens when the base of our exponential function is bigger than 1. When this happens, we're going to get a graph that resembles the following. This graph will have a horizontal asymptote of y equals to 0, but it's going to increase for all real numbers. And by increasing, I'm talking about the fact that the graph goes up as we read from left to right. The other alternative is that our base a is between 0 and 1, like in the previous slide when we had bases like 1/2 or 1/3. When this happens, our graph is going to resemble this decreasing curve, or this mirrored curve from the one that we had above. This graph still has a horizontal asymptote of y equals to 0 and is going to decrease for all real numbers. But in either case, both functions are going to have a domain of all real numbers and a range of 0 to infinity. But it is important to know that an exponential function, simply like f of x equals c times a to the x, there is going to be no real number x for which f evaluated at x equals to 0. In other words, this function has no x-intercept on its own. Unless I start adding or subtracting things to it that would make the graph shift upward or shift downward, the graph alone is never going to cross the x-axis. In other words, our exponential terms are never 0, and they're also never negative. Right now, our general graphing strategy is going to be as follows. Even though we had some XY charts on the previous slide, and in previous videos we've kind of tried to walk away from XY charts, exponential functions, these typically are going to be our best tool. But I don't need to plot so many values. It's enough just to plug in the values -1, 0, and 1 to get an idea for where our curve is going to be living on our x and y plane. We choose these three values, -1, 0, and 1, because computationally they are very easy to work with. Alright, so in this segment we're going to graph for you three exponential functions. Let's first look at f of x equals -3 to the x. Let's do our sign chart with our three test values, -1, 0, and 1. By plugging these into our function, we'll get values of -1/3, -1, and -3. It's helpful to realize that -3 to the x can be rewritten as the function -1 times +3 to the x. That negative sign is tricky because that's not the thing we're taking to a power. You'll never see an exponential function whose base is negative, just by definition. So when you see symbols like -3 to the x, always remember that that is -1 times +3 to the x. But once we plot all these coordinates and graph them, we're going to get the following shape. What we're trying to communicate with this example is that even though I'm seeing the correct exponential curve shape that I should be seeing, it looks like it's a regular exponential function that's been flipped upside down. That's actually what that -1 out front is doing to this function. It's taking all the actual values that I would have gotten from just 3 to the x by itself and making the outputs negative. This gives us a flip about the x-axis. Once we start drawing all kinds of different exponential curves, we'll see that we're essentially just taking the same classic shape and manipulating it by flipping it or shifting it throughout the xy plane. And that's what that negative out front is actually doing for us. Alright, so moving on, we have the function g of x equals 2 to the x minus 2. We'll see that this subtraction of 2 after 2 to the x is just going to take what the original graph for 2 to the x looked like and shift it downward by 2 units. To see this, we'll go ahead and plot our test points, -1, 0, and 1, which output values of -3/2, 1, and 0, respectively. Plotting these points on the plane and tracking this curve is going to give us the following shape. Now, if you go back a couple of slides, you'll see this is the exact same shape we would have gotten for 2 to the x by itself, but I have moved it down by 2 units, which means that my horizontal asymptote has also been downshifted by 2 units. So we've seen two kinds of transformations, as they're called here. First is that when I multiply a function by a negative, it can flip it upside down. Second is if I add or subtract a value from something like 2 to the x, it can take the graph of 2 to the x and shift it up or shift it down by a certain number of units. And this also means that my horizontal asymptote sort of goes along for the ride. Our last function, h of x equals negative 2x plus 1, sort of has both transformations happening at once. I have a negative in front of 2 to the x, which will flip it upside down, and I have that plus 1, which will move my graph up by 1 unit. So taking all this into account and plotting a couple of test points, I'll get the following ordered pairs, and then I will fill in the curve with a sketch. So here I have my 2 to the x graph, which looks like it has been turned upside down and then moved upward by 2 units. In this case, we're going to see that we have a horizontal asymptote of y equals to 1. In general, it's not too hard to figure out what the horizontal asymptote of an exponential function is going to be. We always have a default horizontal asymptote of y equals to 0. But if ever I'm taking an action like subtracting a 2 or adding a 1, that's actually going to give me the real value of the horizontal asymptote. For g of x, when I see that minus 2 outside, that says that my horizontal asymptote of y equals 0 was downshifted by 2. For h of x, that addition of 1 means that your original horizontal asymptote of y equals 0 became y equals 1. Alright, in this next segment, we're going to talk about exponential equations. For a motivating question, let's think about the equation 2 raised to the 3x plus 1 equals to 2 raised to the x minus 2. In a situation like this, how on earth would we solve for x? We know that from linear equations, we're generally trying to isolate variables on one side of the equation until we can get a solution for them. But we can't really do that right now because our variable x is trapped not only in one, but in two exponent locations. So we sort of have to break them out of those locations so that we can isolate these variables. We're going to use the following algebraic rule to help us out here. Suppose that I have an algebraic expression, little a to the big A equals little a to the big B. We have two exponential terms that are equated to one another, and they have the exact same base. And whenever this happens, we can equate the exponents with one another. So at the end of the day, the best way to think about the strategy is when I have like bases, I can drop the bases and just equate the exponents. So looking at our original equation, 2 to the 3x plus 1 equals to 2 raised to the x minus 2. These two expressions have the exact same exponential base. This means that we can drop the bases and equate the exponents and get the linear equation 3x plus 1 equals to x minus 2. And this has a solution of x equals to negative 3 halves. Ultimately, we refer to this strategy as making the bases match or just simply matching the bases. But what if the situation started out a little bit differently? Suppose that I had to solve 2 to the 3x minus 1 equals to 4 to the x minus 2. Right now, the bases are no longer the same, so I can't just equate the exponents like I did before. However, I do know that the right base of 4 can be rewritten as a power of 2. Namely, I can express 4 as being 2 squared. This allows me to transform my current equation. I can take the original, 2 to the 3x minus 1 equals to 4 to the x minus 2, and I can replace that 4, in parentheses, with 2 squared. Now I have a situation where I have a power to a power, so I'm going to take those two exponents and multiply them by one another. In other words, I'm going to multiply the exponent of 2 with the linear expression x minus 2. And once I simplify all my terms in the exponents, I'll get the equation 2 to the 3x minus 1 equals to 2 to the 2x minus 4. Right now my bases finally match, so I can drop the bases and equate the exponents. I get the linear equation 3x minus 1 equals 2x minus 4, which will have a solution of x equals to negative 3. Ultimately, the strategy that we're showing is the following, that we sometimes need to work with the bases to make them match one another. For this equation, I had a left base of 2 and a right base of 4. Since I was able to recognize 4 as a power of 2, I was looking at the number 2 as a common base, so to speak. And once we realized that, the goal became make every base a power of 2 and then algebraically simplify all the exponents. These next two examples show us how to actually locate the common base between two expressions. Let's look at the equation 1 over 9 to the x plus 1 equals to 18 raised to the 2x minus 3. Pause the video for a moment if you need to and try to think about what that common base might be. When we think about it long enough, we might realize that a common base of 9 would be very helpful here. Notice that 1 divided by 9 can be expressed as 9 to the negative 1, and 81 can be expressed as 9 squared. So we're going to take our original equation and make these replacements. I'm going to take 1 over 9 raised to the x plus 1 equals to 81 raised to the 2x minus 3, and transform the left and right hand sides so that I get 9 to the negative 1 raised to the x plus 1 equals to 9 squared raised to the 2x minus 3. Now I'm going to multiply all of my exponents together and simplify. This is going to give me 9 to the negative x minus 1 is equal to 9 to the 4x minus 6. Now that I have a common base of 9 on both sides, I can go ahead and equate the exponents. This gives the linear equation negative x minus 1 equals to 4x minus 6, which when solved has a solution of x equals to 1, and we're done. So just to play the what if game, what if I instead had recognized a common base of 3 instead of 9? I would have gotten the exact same answer, because I could have replaced 1/9 with negative 3 raised to the negative second power, and I could have replaced 81 with 3 raised to the fourth power. You would have ended up getting the exact same solution, and as an exercise, I would encourage you to try this on your own. For our last example, look at the square root of 2 raised to the 2x plus 6 equals to 32 raised to the x minus 4. Take a moment to pause the video and ponder what the common base could be in this example. After we think about it for a bit, we'll find that the common base is going to be 2. I can rewrite the square root of 2 as 2 to the 1/2 and 32 as 2 to the 5th power. So I can go ahead and make these replacements. My original equation can be transformed into 2 to the 1/2 raised to the 2x plus 6 equals to 2 to the 5th raised to the x minus 4. Once I multiply and simplify my exponents, I'll get 2 to the x plus 3 equals to 2 raised to the 5x minus 20. Now that my bases are the same, I can equate the exponents to get a linear equation, which we'll find has a solution of x equals to 23 divided by 4. Now, matching the bases won't always work for us, because sometimes I'm going to have an equation where bases don't match very nicely. Section 6.5 talks about how to deal with this situation. But just think of this now as an introduction to exponential equations, where the nicest and probably easiest strategy that we can have is the one where we have a matching bases situation like we did in the previous 3 examples. Alright, well thank you so much for watching, and we'll see you in section 6.3 on logarithms and logarithmic expressions.